Okay, everybody, we are here for the first session. I'm really excited to introduce to you Manuel Mercier and Madison Elliott. Walter has been here, but we have some browser issues. He'll be back. Yes, so let me tell you a little word about Manuel Mercier, whom will be talking first. Manuel is a long ago friend. We've been studying about at the same time. He was actually one who introduced me to the whole cognitive science world. And he's been doing his PhD in Genève and then has been moving around to New York and in Toulouse. And he's now established in Marseille, where we are. And I think that's it. Manuel, perhaps I can just let you go on now with your presentation. Can you bring your presentation on screen?
Yeah, it's coming. Here we go.
Okay.
Everything is fine on your side?
Yeah, it seems like I have an echo. I'll just reload my page and you should be fine. You can start, Manuel, once your presentation is like this. Okay. Go ahead.
Thank you, Max. And hello, everyone. I'm really happy to have the chance to start this series of talks on good scientific practices in EEG and MEG research. To begin the session on human factors, I'm going to explore with you cognitive biases. Oh, everyone is fine. Don't worry, it's just kids in the street.
Here, everything works fine.
Okay.
Echo again.
So a couple of years ago.
Say yes for echo. Excuse me. Say yes for echo. No for no echo.
Everything is fine on my side.
Okay, go ahead. Allez, vas-y.
Okay, so a couple of years ago, I started to read about cognitive bias and to reflect on it. And there are several things that amazed me about it. First, as you can see on this attempt to classify cognitive biases, there are plenty. The second thing that surprised me was that the more I learn about cognitive biases, the more I see them, really everywhere. And in fact, even if I can identify some of them, I cannot escape to experience them. Even if I know about them, even if I'm doing research on the brain, I am a human being and cognitive biases are part of my subjective reality. The one thing we can do, though, is to learn how to deal with them because they are part of us. With cognitive biases, it's like with visual illusions. Here we see a gray bar, and now we see the same bar, but it's not uniformly gray anymore. We know it's induced by the surrounding gradual change, but still, we cannot avoid to experience the illusion. In fact, it goes beyond this analogy, as perceptual biases can impact our research practices. It's like when we use a jet color map, which was for years the default color map in MATLAB. On the bottom is a grayscale rendering of the jet color map, which highlights luminance boundaries that are not present in the color map on the right, which follow a luminance gradient. Here are represented the same time frequency data. We can see that while the gray color map represents truthfully the data, the jet color map creates some artifactual white contours. What is fun is that this bias was explained to me by a good friend of mine who is colorblind. I then understood why, when we were looking at the exact same time frequency plot, we were not seeing the same results. There are many other things that vision science can teach us about data visualization, as Madison Elliott will tell us in the next talk. Even in the absence of visual bias, data representation strikingly influences our interpretation of experimental results. In a simple graph depicting the relationship between two variables, we are tempted to make inferences, such as the existence of clusters or of a correlation, or even to think about causation. As it will be discussed in the live LiveMEEG session on statistics, defining sample size is critical, not only to reach the adequate statistical power, but also to avoid being fooled by perceptual bias. Here is an illustration on how different representation of the data can lead to different interpretation. Either the entire population shows a negative correlation, or subgroups of the population show a positive correlation. As you can see, the choice in data representation is critical to correctly represent the content of the data. Many perceptual biases stem from some Gestalt principles, which illustrates that we are quick pattern recognition machines and how it can influence our cognitive processes. We have a natural tendency to perceive meaningful patterns, even if those do not exist. We are simply wired for pareidolia. We all see here an eye before realizing that it is a zinc emptying. I don't know what you see on this cloud on the right, but some of my friends see a bird, while I see subcortical structures. I must be biased. Some of the same Gestalt principles that affect perception can affect our reasoning, can lead to build stereotypes and make us good storytellers. Now, let's take a concrete example. Let's use a map indicating a disease rate to Bob, a fictional character. The numbers reveal to Bob that the disease rate is lower in areas with the following characteristics. They are rural, sparsely populated, and traditionally conservative. One story that easily comes to Bob's mind tells him that lower disease rate is due to the healthy lifestyle in the countryside because of reduced pollution and access to healthy food. However, if Bob would have first looked at the areas where the disease rate is higher, he would have found other areas, but with exactly the same characteristics: rural, sparsely populated, and traditionally conservative. Then the easy story would have been, okay, this high disease rate is due to bad access to the health system or to bad diet habits. But actually, there is absolutely nothing causal in the datasets. In both cases, we are dealing with sparsely populated area. And thus, the mathematical explanation tells that we are more likely to encounter extreme values in some small samples than in large samples. In fact, in this example, when building those two stories, Bob selected the first and wrong characteristic of the areas. He neglected the second characteristic, which was the right one actually, and Bob probably quickly judged that the last characteristic was not relevant. Why the political inclination would have any influence on a disease, right? Then Bob built a coherent story based on stereotypes, story that implied causation. And each of those steps correspond to a cognitive bias. Formally, a cognitive bias is defined as a systematic pattern of deviation from reality or rationality, which can relate to perception, logic, memory, social behavior, judgment, or decision-making. So why do we have them? What do they serve for? Our brain receives a huge amount of inputs. Also, to avoid information overload and permit quick reaction, our brain uses shortcuts or rule of thumbs, but it can cause some distortion. Now, I would like to review some cognitive biases that can slip in our practice of MEG research. We have seen in the example with the disease that our brain is subjected to focusing effect and selection bias. The same happens when we perform multiple tests on our data. We tend to overthink and often only report the test that was significant and overlook the ones that were not. We also have seen that correlation is not causation. However, it is often the case to mistaken a functional cognitivity result for a directed functional cognitivity result. In the former, there is no causal measurement of causality, which is the case for the latter. Another bias example is the inductive bias, which is important to keep in mind in machine learning. Basically, it means that the testing dataset can only be classified based on the features defined from the learning dataset. After the learning phase, everything becomes somehow a learned nail for the hammer algorithm. Here, I'm not saying that machine learning is not a great tool, but as any method, we should keep in mind how it works. Next Wednesday, Karim Djerbi will tell us more about the good practices and pitfalls of machine learning. Cognitive biases also have an influence on the progress of science, and they can lead to circular reasoning or double dipping. This is nicely illustrated by two cognitive biases. The first one is called the confirmation bias. That is the trend to search for, interpret, favor, and recall information to confirm a belief. The second one is the insight bias. That is the tendency to perceive events that have already occurred as having been more predictable than they actually were before they took place. These two cognitive biases directly relates to our way to follow the two main research procedures. The first one is the post-diction procedure. There, we start with the existing data, on which we conduct exploratory analysis to generate a hypothesis. This is the context of discovery. The second one is the prediction procedure, where we collect new data to test a hypothesis. The analysis will be, therefore, data contingent. It is a confirmatory research. This is the context of validation. And it is a cycle between the two approaches that permits to improve a model of brain process, for instance. In the next session, I would like to focus on some biases that became more important in the last decades, with the race for grants and high impact publication, the celebrity status of some researchers, and the supremacy of some theories. The odd-end fallacy, that is the belief that a person who has experienced success has a greater chance of further success in additional attempt. Maybe it reminds you some grant selection procedure, no? The second, the self-serving bias, is the attribution of success to one's own abilities and effort, but attributes failure to external factor. Easy, right? The last one, the bandwagon bias, occur when someone accepts ideas that are already adopted by others. While I was saying that cognitive bias are inevitable, we can try to avoid them in our research practices. For instance, by thinking twice and slow. This is the topic of the talk on the slow science movement that will be given by Isolt H.R. Prichard next Friday. Of course, learning about cognitive biases helps to be aware of them in order to detect them. I especially recommend those two books and authors from social science and economic sciences. A funny way to detect biases then is to organize with your team, your project team, a pre-mortem meeting. So what it is, basically, before starting a project, imagine together with all the team that the project has failed. Then work backwards to determine what could have led to the failure. Another good trick is to keep track of what you do. For instance, it helps to avoid to evaluate the quality of a decision based on its outcome. And do not forget, be skeptical, especially towards anything that feels grounded. Indeed, once we have accepted a theory and we are using it as a tool in our reflection, it is extremely difficult to notice its defect. Just think about the blind spot. We never see it, but it's always there. Okay, I stopped here, hoping that you will enjoy the gameplay of Cognitive Biases Hunt. If you want to know more about data visualization and common fallacies, stay tuned to listen to the upcoming talks and to the following roundtable. Thank you very much for your time. And thanks to the LiveMEEG team and all the people who helped us to organize this amazing event. Thank you.
Yes, thank you. I feel a bit lonely now. I feel a bit lonely clapping, but I'm sure everybody is clapping in the back. Thank you, Manuel. Great talk. Bravo, bravo. Okay, and well, it seems like the question bar is really not yet working. We have a lot of applause. I hope you see it, Manu.
Thank you, everyone.
Okay. And okay, I think your talk was really clear. That's what everybody says. And so in the interest of time, we will move shortly to Madison's talk. Before that, let me answer the question that everybody was asking, that many people have been asking about knowing whether it will be possible to review to see these talks again. Yes, you just come back to this very page and you will see this very talk. It works for all of them. Okay. All right. So Madison, thank you for being here and for accepting our invitation to join us. You are, as far as I know, not an expert in EEG, but rather someone who examines visual properties and how to use vision to represent data. You're a PhD student in particular with, remind me his name escapes me right now.
Ron Rensink.
Voilà, Ron Rensink, who was earlier, a few years back, showing some very interesting aspects of this research that you're showing. And well, I can just let you speak now. Can you bring your presentation on screen?
Sure thing. Okay.
There it is. Okay. Okay.
So thanks so much for having me today. Really excited about being at an EEG conference because, as Max was saying, I am definitely not a primary EEG researcher. Collaborated with some EEG work in the past. But I'm here to talk to you today about what vision science can teach us about best practices in visualization. So how we can be good data designers just based on knowing a few simple kind of vision science 101 tricks. So a little bit about me, as Max was alluding to, I am a PhD student working with Ron Rensink at the University of British Columbia. I'm a vision scientist and a computer scientist. I co-founded an interdisciplinary research group called InfoViz Cross Vision Science, which seeks to promote collaborative work between computer scientists and vision scientists. In the summers, I work for Google Health for a team that builds AI models to detect cancer in CT scans. So I do a bit of work with medical imaging, but mostly I spend my time thinking about the perception of correlation in multi-class scatter plots for my dissertation. So information visualization, what is it and why do we care about it? InfoViz is basically the graphical representation of data values that help us understand that data better. Right? It's really hard to do things like rank order these raw values in a table, but when we visualize them as a bar chart, we're able to extend our cognitive abilities and our visual abilities, which makes us better thinkers and seers. We can use visual information to draw insights, analyze, learn, make decisions, and many more things. And what is vision science? Vision science is the study of how vision works and is used in day-to-day life. It includes visual attention, so how we guide our attention around the scene. It includes visual memory, how we hold on to information and encode it. And it also includes visual intelligence, or how we make decisions or analyze information. And of course, our visual system is the most common sensory modality that we use to perceive visualizations. So it's no surprise that vision science offers us a really great foundational toolkit for understanding data visualizations, and that we've had many breakthroughs from using the methods that we use in vision science research to try to understand as well as improve visualization design. If we go back to what is now an ultra classic kind of computer science InfoViz paper, Cleveland and McGill, 1984, they use these kind of psychophysics-esque tasks to show us things like sometimes you use bar charts in place of pie charts in certain scenarios to help people discriminate values. They kind of lay the foundational principles for information visualization design. And ever since then, vision scientists and collaborative researchers have been super interested in adapting modern psychophysics methods to study visualizations more deeply. So in 2017, Danielle Safer ran a bunch of discrimination tasks where she was able to show that mark size really matters. So when you're choosing the color encoding for your visualization, she notes that you need bigger color differences the smaller your stimuli are. But I'm here to say that you don't need to be an expert in visualization research. You don't even need to read the full catalog of these interdisciplinary papers in order to become a great designer. All you need to know is Vision Science 101. You just need to know a few of the seminal works about how the visual system functions, and you can easily extrapolate and apply these rules to be great data designers. And so I'm going to talk about 3 of these rules today. The first is that working memory is capacity limited. So our visual system can only hold a very few numbers of items in working memory. And that number is probably around 3 or 4, although, you know, depending on the vision scientists you talk to, they'll have a very different theory of the details. The second rule is that salient targets are found more easily. It's much easier to find this large orange dot around all these small red dots than it is to find the same size orange dot amongst similar warm-hued dots. And finally, the third rule is that our brains summarize sets of information. So much like Manuel was mentioning, our brains capitalize on heuristics and scene statistics. And what we're constantly trying to do is summarize information. So it's very easy at a glance to notice that the dots on the top go from lighter to darker as you move from left to right. And likewise, the dots underneath of them move from smaller to larger as you move from left to right. And we can notice these trends without even needing to deploy attention to every single dot in order to understand that information. So the first question that you should always ask yourself as a designer is, what is the goal of your data visualization? And here's 3 important questions that I've kind of pulled out of a textbook from Tamara Munzner, who's an information visualization researcher. 3 questions that I want you guys to always ask yourselves are, is this a presentation or is this a data exploration? Is your target known or is your target unknown? And are all of your data relevant, or is just a subset of your data relevant? And so for the first issue of exploration versus presentation, if I'm exploring my data, I want to get a full view of it, and I want to have large contrast. So, you know, I'm not saying that every exploration needs to be a heat map, but you want to be thinking about, you know, showing yourself as much information as possible and giving yourself every opportunity to use those salient search skills to find the relevant info. But by the time you're wanting to present it, you probably just want to pick a subset of values, and maybe you even want to translate to a different encoding so you can maximize people's abilities to, say, discriminate length here to see the significant trends. Which brings me to my point of all data versus a subset of data. You know, if you're considering all of your data, you might be looking for things like trends, like a line chart could be a really good choice. And if you really care about comparing every single point serially, there's no need to focus on anything. We're using our summary skills here to understand that this is kind of a wild trend. It's got some highs and lows, but generally seems to be increasing as we move to the right. Of course, if it's just a subset of data you care about presenting or you care about analyzing, just visualize that subset. Don't be afraid to derive values or to translate your encoding when you're visualizing it for presentation. And finally, is your target unknown or is your target known? So if your target's unknown, you're probably going to be using a browsing process visually, right? We might be relying on either a search pattern, we're using our salient detection skills, or we could be relying on some kind of summary pattern. But if your target is known, you definitely want to flip yourself or your viewers into more of a search mode. So you want to be depending on our ability to identify salient or different features and highlight that in the encoding that you choose. We also want to consider what knowledge we have versus what knowledge our viewers have. So Cindy Zhang, who's a longtime collaborator of mine, has this awesome experiment where she starts all participants with the same chart. So she says, everybody, this line chart, it's about political performance leading up to an election. And what she does is she tells people 3 different stories. So she breaks her participant population up into 3 groups and tells them 3 different stories about this data. And what happens is when people are given background information that leads them to see one pattern in the data as visually salient, right? So she tells them this story about something happens at an initial debate, and then one candidate's popularity rises or decreases, and then something happens at a second debate, like one of the contenders insults the other's wife, which leads to another change in the trend. People perceive this, these patterns as visually salient at different points in the story, depending on what she's telling them. And then she asks these viewers to predict, with naive viewers, what she thinks they will find, or what they think the new viewers will find salient. So she's telling people a story, she's giving them some kind of primer or impression about the data, and then she's asking them to predict what the next person is going to think about this slide chart. And they're very explicit that they say, okay, this new viewer won't know this story. They're just looking at the lines. So what do you think they're going to pick up as salient in the lines? And perhaps unsurprisingly, everybody circles the things that they were just told are salient. So depending on the story that you tell people, they predict that the next viewer will see something totally different. Basically, individuals are strongly influenced by their own knowledge. And despite explicit instructions to ignore that knowledge, predicting what others would find to be salient was sort of like unsuccessful and completely dependent on the story that they carried. And this result reflects a psychological phenomenon which is demonstrated quite often in cognitive reasoning literature. That's called the curse of knowledge. So definitely beware of the curse of knowledge as you are designing displays for presentation. So quickly, I want to put it all together for you. So I want you to consider your viewer task or goals, right? If we're discriminating or rank ordering discrete values, I'm going to give you an example where we might want to discriminate or rank order discrete values, and we could choose a pie chart encoding here. So one thing that's hard to see in this pie chart, perhaps, is the difference in values between this small purple slice and this small green slice. If you're just trying to rely on your visual system here, it may not be exactly clear which one is larger, which one has a bigger piece of the pie. But maybe if I add this legend, then perhaps it's easier for you to understand the difference. Although you're probably maybe surprised that the legend doesn't help you so much. And that's because our working memory is highly capacity limited again. So our working memory actually sort of gets wiped clean with every eye movement. So even just the effort of going back and forth and referencing this legend is going to be quite annoying and cognitively burdensome for our visual system. But if we were to instead encode this in a bar chart, suddenly it becomes a lot easier to make this specific comparison. And we're able to see that this purple slice is quite obviously larger, no reference to the legend values needed. And that's because length is quite a salient low-level feature. And of course, salient targets are found or even compared more easily. Another important consideration to make is the part-to-whole comparison versus discrete comparisons. And so here, if we have our average transaction type by payment type visualized as a pie chart, it's actually misleading information because these are all averages, meaning that they're discrete values and they're not adding up to 100%. So the bar chart sort of wins out here again, not just visually, but also actually for making a decision about this data. And this is especially confusing because our brains, again, summarize sets of information. We want to see the whole here in this pie chart. We want to assume that this is 100%. It's a little easier to separate ourselves from that idea when we're comparing these discrete values in the bar chart. So I want to offer some additional pro tips and considerations before I close here. Some presentations to ask yourself, was an algorithmic solution obtained? If so, you may not even need a visualization to help you understand the data, to present that result. Are you highlighting a meaningful artifact in the data, right? Is this just one thing that you need to show, or is the whole important? And finally, does the viewer know and understand your signal? Do they even understand what you're trying to present or the story of how you arrived there? Because if they might not, Ben Schneiderman has a great mantra of visual information seeking for you to follow as you build out or even unwrap your visualization in a presentation. And this mantra says you should start with overview first, then zoom and filter, and then give details on demand. And what that means is you show all of the data first, you zoom and filter on the next most relevant part, and then finally, the last thing you reveal are those details. And this gives people a really nice visual story. It allows things to feel very cognitively and perceptually complete by the time you're revealing those small details. And so thank you so much for having me at this conference. Thanks for listening today. If you're interested in this kind of interdisciplinary research, check out VisX Vision's work at both IEEE Viz and VSS. And if you're interested in this kind of design work or just want some cool tips, I've put some links here to some of my favorite pages for data design inspiration. Great, thank you so much.
Bravo. Thank you, Madison. This was a great talk, and everybody is appreciating it. I think we have actually a question, a direct question for you, and I should be able to invite Aina Pius, who actually asked this question on screen. Let's see if that works. If not, I can ask it for her, but it's nice to have people jump in, and I happen to know Aina, so it would be nice to have her on screen. Salut, Aina.
Salut.
Hello.
Salut. Thank you, Madison, for your talk. And I'm come from a vision background too, and so it's just so nice to have someone like you come on and explain things. Now, I have a question for you, which actually many presenters in this conference may well have. What advice do you have for those of us who are now have transitioned from going face-to-face presentations at conferences to presenting stuff online? What do you do differently?
So this is outside the realm of perceptual. Well, it's not totally outside the realm of perceptual tips and tricks, but actually this is a Ben Schneiderman tip too, is think about designing everything for mobile. So make all of your graphics super big, and also make all of your narrative points structured in like sort of these 1 to 2 minute chunks in your presentation, because I think what you can assume is that everybody that's virtual also has like 50 browser tabs open and possibly multiple monitors. So the more salient you can make your information and the more concise you can make your kind of like narrative conclusions on each set of information you're unrolling, the better. Unfortunately, everybody has the attention span of like a gerbil right now. And so whatever tricks you can use both cognitively and perceptually to combat that, I would definitely advise going with.
I'm going to use that quote, attention span of a gerbil. I love it. And thank you for that advice, which I'm going to follow when I give my talk tomorrow.
Yeah, thanks for your question.
Okay, thank you, Aina. Okay, thank you very much, Madison. I think this was very interesting and a nice talk. We can see from the reactions. I have just one more question since we have a little bit of time. It is a real difficulty for us because we have so rich data to really be able to represent data for exploring versus presenting. And I found it very interesting how you balance these two types of visualization purposes. And but I wanted to say how. I wanted to make the point that it's very important to still even if we're representing just to communicate results, it's always very important to still give the viewer an idea of the amount of noise that was present in the data. So error bars, of course, but also sometimes, you know, like representing the baseline. And yeah, I wonder if you have a comment. That was more a comment I wanted to share. Do you have something to say? I mean, you don't have to, but.
Yeah, I just am going to bring up this slide again because I think this mantra of information seeking is so powerful, and I didn't have time to go into it today, but it actually does follow even the way that our brains and our visual systems kind of breaks us down. So don't be afraid to tell the story with your data from start to finish, right? You know, that curse of knowledge bias, I think that gets a lot of EEG researchers in particular into trouble, right? Because you sort of assume that everybody's used to understanding the fact that you've just cleaned all of your data, you've removed all these artifacts, and now you're just showing the relevant pieces. But for like a more naive viewer, someone that might not be familiar with like the process that you use to clean that data, really starting with like the raw set, even if that's not the point, zooming and filtering, and then giving those details on demand, unrolling that like a story through your slides or in a dashboard or a series of visualizations can be so powerful and really just help people feel like cognitively complete with the story that you're telling them. Even if they don't understand every nuanced detail of how you went from A to B to C, at least you're giving their visual system and their cognitive system something to like anchor onto at every step of the way so they can understand a little bit of where the magic comes from.
Okay, great. Thank you for this answer. All right. So, well, actually, you know what? While we managed to get Walter back on screen, we have a 10 minutes break. And in this 10 minutes break, I don't know, I was thinking perhaps actually there were a few questions that came up afterwards for Manuel's talk. And perhaps it would be right now a good time to ask them. And let me read the questions aloud. What would you voilà, exactement. Manuel, what would you suggest? Or actually, can we invite that person? I like the thing of having people come on screen. Let's see if that works. Marco Redo is perhaps coming on screen right now to ask their question. Okay, it's not coming. What would you suggest, Manuel? Let me go start answering. I'm getting used to the whole
to the interface. Yes. Actually, I have an answer, but here we go.
Coming. Hello.
Hi, can you hear me?
Yes, we hear you very well.
Okay. Hi, thank you very much.
Can you ask your question?
Yes, thank you. So after your talk, like, by the way, thank you very much for that. It was very interesting. I found myself like, well, very, I don't know, like it happens to me a lot when we have to prepare an experiment that you should think about everything that can go wrong or that can be external factors that can lead to misleading factors during your experiment. And I was thinking maybe you could share some suggestions on how to do this process in the best way possible.
That's a tough one.
So.
Yeah, I don't think I have the answer, but Antonio Schedito, who is going to present, who is going to be with us today, and I think on Wednesday, he said he invited you to go to his presentation. He's going to talk about the open science framework and all these things. So I think there are some great tools that helps. I was mentioning this kind of a strange meeting, like the Morty meeting. It's much easier for us to see the what's wrong, like outside of us. Like if we can see, if we discuss with someone, we can see the default or the positive things of that other person, but it's much harder for ourselves. That's a little bit the idea of that meeting, like by meeting with the colleagues and try to think all together what is going to to be wrong, I think it's a nice way to set the thing in advance. One important thing that I didn't mention during the talk is that idea of meeting. What is even better is not to discuss first, but everyone think and write down on a piece of paper, and then you start the discussion. That way, there is no influence between the members of the meeting. And I think, yeah, we always think better and we go further if we are a group of people and if we respect the time of, the thought of the others. I think that's one way, and there are plenty. There are some tools that are accessible. And there is also some other talks that will come later. In the EEG and MEG community, you start to have some kind of benchmark, like what you should do, which is like all the, basically it's like a checklist. What you have, it's good to verify before you move on. So that's my long answer.
Thank you. That's a good tip.
Satisfactory.
Yes, very much. Thank you.
This is great. Thank you so much. Now I will take you off the screen.
Thank you.
I think we are right on time to move on to the next and last talk of this session. Walter, hello. I am very pleased and excited to have you here, because to me, I told you as I was inviting you, right? To me, you are the face who told me about reasoning and making inferences properly and understanding arguments because of the course you taught on Coursera. That's probably a few years back. I mean, by the time I saw it, it was in 2015 or so on Coursera. And this was really, to me, a shock, this course, as much by the content as by realizing that I had never been told anything of any of these things in my course. I am a biology background, and in biology you learn about molecules and the cells and everything, but never about how to reason properly and how to make the right decisions and how to convince people and so on. And I was really amazed. I guess that in other fields it's much more common, and that's perhaps the 101 psychology or philosophy course that people hear. So I'm really happy that you accepted my invitation, even though our fields are quite far apart, and I guess you must be solicited quite a lot. So thank you very much, Walter. It's really a great pleasure for me to have you here, and I guess for everybody to listen to you talk now. Thank you.
Good.
Yeah.
Well, thank you very much. Can you hear me?
We hear you very well. We need your presentation on screen.
How do I share my screen so that I can do the slides?
So you should have
I apologize for my
That's
technical difficulty here. I'm going to put this over to the side.
Yes.
When we did this during the practice session, this worked.
Okay.
Can you see it?
Adrian just told me that you are still using Safari.
No, I am now on.
This is Firefox?
I'm on Firefox.
Firefox or Chrome. Okay. And now this little share button below your face on screen.
Yeah.
You try to toggle it.
Yeah, it just says my name.
Yeah, that's perhaps actually at the top, above your hair here.
Okay, sorry. Toggle.
There's a share screen, a small icon with an arrow.
Well, I've got to do it over on the right side, though.
Okay.
Share screen.
That's okay. We're not live anyway. There's not like 452 people in the room, right?
Huh. Okay. Share screen. Okay. It says no camera, microphone. Let's try that. Let's Still no camera
If
microphone.
that doesn't work, you know what? Adrian just sent me your presentation that I guess you sent him before. So
Okay.
perhaps I will be able to show it, and you just say slide, and I slide. I change the slides. Okay. So let's try that. Okay, let me download it. Track, ouvrir comme ça. Okay, I hope I can share my screen. Okay. And I share the screen. We will see application window. This guy should do. How is this now? Do you see my screen?
I do, yes.
You do? Then I guess others must see it too. And like this too?
Yeah.
Okay.
So it
Then you
says
just tell me when I need
fallacies.
to. You just tell me when I need to switch. Okay.
Okay. Good. So first of all, I wanted to thank you for inviting me. I want to warn people. I'm a philosopher. I'm not a scientist, and so I'm going to be talking not so much about the gathering of data or the analysis of data, but instead the interpretation of data. Once you've got results, what do you make of them? How do you figure out what follows from them and what you should believe about them? And what I'm going to try to do is to point out some very common fallacies. Now, these are basic fallacies that a lot of people commit. They might seem very simple, but that doesn't mean you don't make these mistakes. I make them, you make them, everybody makes them. It's part of human nature to commit these errors in reasoning. And I'm going to try to illustrate them with one particular experiment in the history of science using EEG. So next slide. Namely, an experiment that was done, or a series of experiments that were done by Benjamin Libet many years ago, back in the 80s. He, oops, something happened there.
Yep, that's good. Thanks. Sorry.
He was actually, some people might not know about Libet. He was very famous at the time. He was a physiologist who studied action and consciousness, and he was actually awarded the first virtual Nobel Prize in psychology. I didn't even know there was a Nobel Prize in psychology. Apparently it didn't last for long, but they gave it to him first. It shows a bit about his reputation at the time. The experiments that he did, keep back on the previous one. Mm-hmm. The experiments that he did are illustrated in that little cartoon. He put an EEG cap on people. I think he had 32 electrodes at that point. It might even have just been 16, but it was in the 80s. And he had an EMG on the wrist of his subjects to measure when their muscles in their wrist would flex, because the instructions were simply to flex your wrist at any point you feel like it. Now, that setup had been used before to discover the readiness potential, or RP, as we will call it, which is a brain signal that preceded the motion of the wrist, preceded the EMG signal. What Libet really added was the Libet clock. And there, what you had was a clock, such as on the TV screen in the cartoon, where a cursor or indicator went around the screen at about 2.56 seconds per revolution. And the subjects were told to report where the cursor was going around the screen when they decided to move their hand. They could move it whenever they wanted, but he wanted them to report when they were conscious of deciding to move their hand. And that's what they reported. So next screen. So the results he got were like this. The left two columns were the RP1 and the RP2. The RP, or readiness potential 1, was when they pre-planned when they were going to move. The readiness potential 2 were when they did not pre-plan but just moved without thinking, oh, I'm going to move when the cursor gets to the 9 or something like that. And we'll see the averages later, but these are individual subjects on this slide. The S column to the right will be important for us because there what he did was he pricked their hand and had them report when they felt the prick on their hand. So there was no motion involved in that one. Next slide. When you average all of these, what you get, this is a well-known diagram to some, but I assume some of you have not heard of this experiment, so I wanted to explain it in enough detail because we'll refer back to it. The results were quite surprising because W on this indicates when the person reported becoming conscious of making a choice. Of course, these are averages over 40 trials for each subject. And W there is just the average of the two, but it came to about 150 milliseconds before the actual motion. Then the RP, the brain activity, which looks like it's leading up to the decision and the motion, was starting at 500 to 1,000 milliseconds before. So you had brain activity that was occurring even before the subjects had chosen to act. And this was very surprising to people because you would think that you choose to act and then your muscles start moving as a result of your choice. But actually the brain activity looks like it's beginning before the W actually occurs. That is, before you're conscious of willing to move. Next slide. So our question here is going to be, and I apologize, my slides don't have these little pictures over the words, but somehow the formatting got changed when it was moved to a different computer. The question is, what do Libet's results show? Libet and some of his followers drew three main conclusions that we're going to talk about separately in sequence. First, they thought that the readiness potential, that is the brain activity that occurs 500 to 1,000 milliseconds before the motion, occurs only when there's a physical movement. You know, the argument there is very simple. It didn't occur when there was simply a stimulus in the S condition. The second conclusion they drew was that the readiness potential causes the conscious will because they seem to be correlated and the readiness potential comes first. The third conclusion that they drew was that the conscious will does not cause the physical motion. That's the really surprising one because it seems like when you choose to move, it's your choice that makes your hand move. So everybody thought this was, you know, a groundbreaking, magnificent discovery that led to some people to say we don't have any free will, we're not really responsible for our actions, and they drew all kinds of conclusions off of this. My question is going to be, are these arguments any good? And we're going to look at these conclusions one by one and see whether the arguments really work. Next slide. So the first conclusion is that you don't get an RP when there's no M. There is an RP when there is a movement. There's no RP when there's no movement. So it looks like the RP is very closely correlated with the movement. And the evidence that there's no RP when there's no movement is simply the stimulus case where they stimulated the person's hand and the subjects reported that when they felt it. Okay. Now there's a problem with the first claim, which is that some unusual subjects showed a motion without any RP at all. So when you average across them, there's always an RP, but sometimes, at least on some trials, there were subjects who showed a motion without any RP at all. And that's just kind of left out. Nobody really knows what's going on with that as far as I'm aware. Tell me if you do. But I'm going to focus on the second problem, which is that the claim is that there's no RP when there's no movement on the basis of the stimulus trials in Libet's study. But the problem is we also do purely mental actions. Philosophers have talked about these for a while. I can sit here without moving my body and add the numbers, 35 and 18 and get 53. Well, that's not a physical motion, but it's still an action because I'm doing it voluntarily. Next slide. So what we wanted to do was to find out whether, in fact, we got an RP from these cases of purely mental actions with no physical movement at all. So we instructed people to sit still and look at the screen. And you can see we had a Libet clock with the cursor going around the entire clock. And for the first three, you just had a RSVP screen sequence of numbers appearing randomly in the quadrants. But then you had letters appearing more still. And subjects, when the cursor was between 3 and 12, were instructed to choose one of those. Not do anything, just choose and stand still while you're doing it. And there were other trials where they were told to choose, but also press a button when they chose. And in other cases, they simply reported later where the cursor was when they chose. So we had cases where there was a decision, that's the black line in the upper right, and cases where there was a decision and also a movement, a button press in the upper right. And you can see that the signals that we're getting from those two types of trial were exactly the same. So it looks like the RP is not associated with physical movement at all. Instead, it's associated with decision-making, even when there's no physical movement. Or maybe it's not decision-making, maybe it's something else, but it's certainly not physical movement. Next slide. So this is an illustration of what I want to say it's an illustration of the first fallacy I want to bring out, which is hasty generalization. When you set up an experiment, you always have to pick some types of trials and do a certain set of them. But people often say, well, this is what happened in all the trials in my experiment, therefore it always happens. And they generalize very quickly from the types of stimuli that they used to all RPs in general. So what Libet did is he said, I've got my physical motion trials and I've got my stimulus on the hand trials, and I get the RP in one but not the other. So it must be that RPs occur when and only when there's physical motion. But that's only because he didn't try mental actions. He thought that the trials in his experiment were comprehensive, but in fact they weren't. Now, this mistake happens all the time. I think everyday stereotypes are based on it. You know, you see some members of a minority group committing some kind of theft, and then you go, oh, they're all dishonest, they're all thieves. Well, obviously, that's a bad inference to draw. You should not be drawing that. But scientists do the same thing all the time. So Libet has these very weird actions with people just flexing their wrist or sometimes just moving their finger. And he says, you know, whenever they want for no apparent reason. And he says, oh, well, I've just shown you something about action and free will. The same thing happens in a field that I work more on, which is moral judgments. People will take a certain subset of moral judgments, do an experiment, and now they're going to tell you about the nature of morality. Or people study weird subjects, Western educated, industrialized, rich, and democratic participants, and they generalize to human nature. And I think scientists have to always be very careful about generalizing from the kinds of studies they do with the participants they have and the stimuli that they have to these larger conclusions. Next slide. Next slide. There we go. So that was the first fallacy for the first conclusion. Now, the second conclusion that Libet drew is that W does not cause M. That is, our conscious will does not cause the motion or the movement M stands for. Now, here, it's not clear what his reasoning actually was, but it's easy to imagine several fallacies behind him drawing this conclusion from the data that he had. And his followers doing the same. The tempting argument as well, something's got to cause the motion. It's either going to be the RP or the W, right? It's either going to be the brain activity or the mental act of choosing. And we find that the RP does cause the M in that case. It still might cause it, even if it's, sometimes present when it's not there, because it might have other elements. Therefore, the conscious will does not cause it. So either the RP causes it or the W causes it. The RP does, so the W does not. Well, I hope it's clear that that is a fallacy. It's called affirming the disjunct, because either or is a disjunction. And you can see that it's a fallacy just by going, well, reasoning like that is kind of like this reasoning. Either smoking causes death or lung cancer causes death. Smoking causes death, therefore lung cancer does not cause death. Well, I hope everybody sees how crazy that argument is, and it has the same form as the argument on the top. The reason it's no good is they might both cause death. As a matter of fact, smoking might cause death by causing lung cancer. Well, the same thing applies up above. The RP, the brain activity, might cause the motion by causing the conscious will. And so then the argument, the conclusion is going to be false, even though both premises remain true. You haven't ruled out the possibility of both. Next slide. Another possible form of reasoning in which it seems to occur at some point in Libet's writing and the writings of his followers is to look at the options. So maybe let's look at the data in the upper right again. You say, well, one possibility is that this W, the conscious will, causes the motion, and the RP doesn't cause the motion. After all, it's not always associated. Remember, we saw it also in the purely mental actions. But wait a minute, that means you've got a mental thing causing a physical thing with no physical cause whatsoever. Physicalists are not going to be happy with that. And I, by the way, am a complete physicalist, so I'm not happy with that. Backwards causation is another possibility. Maybe W causes the RP, our conscious choice causes the brain activity, which then causes the motion. But wait a minute, W occurs after the RP. That would mean the cause comes after the effect. That would be backwards causation in time. Now, some people have argued for this on the basis of quantum mechanics, but I don't think that's going to be very attractive anyway, certainly not to me. So then Libet says, well, if those two aren't good, the option that's left is epiphenomenalism, which is that the brain activity causes the motion, and the conscious will is like the steam coming out of a locomotive. It's not what's causing the motion, it's just a side effect. So Libet argues it's got to be either libertarianism L or backwards causation B or epiphenomenalism L, E, but it's not libertarianism because that would be non-physicalist. It's not backwards causation because that conflicts with physics as well. So it's got to be E. Well, obviously what he's forgetting is that there's another possibility. This is called the fallacy of false dichotomy. You're basically overlooking a live option. And in this case, the live option is pretty commonsensical. The brain activity causes the conscious will, and then that conscious will causes the motion. There's nothing surprising about that. So then Libet's studies by themselves don't show that we don't have free will and the mind doesn't cause the body or anything like that. You might think those are true, but these experiments don't show that because they overlooked a live option, which is that common sense interpretation. Next slide. Third conclusion was that the brain activity causes the conscious will. The RP is the brain activity, the W is the conscious will. So here the tempting argument is that whenever RP occurs, W follows later. Therefore, the RP causes the W. Notice that happens even for the mental action cases that we talked about, not only for the physical action cases. So Libet interprets the RP as an unconscious decision that then later causes the consciousness of deciding to do the thing. Okay? But the fallacy here, which was mentioned in one of the earlier talks, so I'll just do it very quickly, correlation does not imply causation. My favorite example is I used to live up north in the United States where I would stop swimming outdoors, usually in September. We had a swimming pool, but I would close it down And then the next month, the leaves would drop off the trees. But that obviously doesn't mean that my stopping swimming is what caused the leaves to drop off. So I hope that's pretty clear. But there's a trickier question, which is, does causation imply or require correlation? If it does, then the lack of correlation is evidence for the lack of causation. Next slide. So what we did to test this is we said, wait a minute, all of Libet's experiments are averages over 40 trials. So we replicated Libet's experiment in a new set of 20 subjects, and we took 40 trials for each of them. But let's look at the early W trials, that is, when the person reported consciousness of will early, and the late W trials, when they reported it late, and see whether we also have the early RP trials, where the RP deviated from the baseline earlier, and the late RP trials, so just do a median split on both of them. And now the question is whether the early RP trials are associated with early W trials, and the late RP trials are associated with late W. And the answer is no, not at all. If RP causes W, then the early one an earlier cause should mean the effect occurs earlier, in this circumstance at least. And the late RP should be late W, but that's not what you get. Haggard had actually found this in an earlier study, and we replicated what Haggard found. But Haggard claimed it's not the RP, it's the LRP. Next slide. Where you're comparing C3 and C4 on the left and right sides, and subtracting one from the other. Well, okay, he thought there was a correlation, but we found no correlation using more subjects and a better statistical analysis, better in my opinion. And so it turns out that it's not correlated either with the LRP and the W. So we're left finding that it doesn't look like either the RP or the lateralized readiness potential, the LRP, neither of those is what causes W. So what's going on with W? That's the question. That's our consciousness of will. Which part of the brain is associated with that? Next slide. My conclusion is, well, we don't know. The only conclusions we can draw from all of this is that we need to learn to spot these fallacies in arguments when we're trying to interpret our data in order to avoid mistakes and exaggerated conclusions. We don't yet know what conclusion to draw from Libet's experiments. They've been replicated many, many times, but the interpretation is very tricky and difficult because people keep making these kinds of mistakes. And more generally, I think it's important for scientists as well as philosophers and everybody else to recognize that we really just don't know nearly as much as many people think they know. And pointing out these fallacies is one way of making us more humble about the kinds of conclusions we can draw from our experiments. So that's my my general lesson, and I look forward to your questions.
Thank you so much. And I hear my echo. Okay. Thank you very much, Walter. I think I was told, though I couldn't see it because I had the screen on, I will have a few questions. Okay, you guys should upvote the questions you think are interesting. I think we have a few, and this is great. Let me invite one speaker, one question on screen. Check. The thing is that since we had the three talks in the same session, the questions don't all apply to your talk, Walter. So let me try to invite.
That's okay. No, if people want to ask the others questions too, it's fine with me.
Yeah, we will anyway switch to the general discussion in a moment. But I just wanted to see if there were any pressing questions for you right now. And Claudio Babiloni will be coming on stage. Will he? Oh, his question disappeared. Okay, well, the question disappeared, and I don't recall what it. Ah, no, there he is.
Can you hear me?
Yes.
Yes.
Claudio.
Yes, congrats for the organizer to organize this fantastic meeting. Cool. And this outstanding presentation from the speaker. My comment is that your nice control experiment with the decision without overt movement can be related to several parallel processes, including decision making. But one aspect that we know is that the motor imagery can develop a reduction of alpha rims over the motor areas and also readiness potential. So how can you take the difference between neural basis of decision making to perform a movement, a voluntary movement, and the simple imagination of the movement in your control experiment?
So that would be a very interesting experiment, I think, to look at the similarity of imagining moving your wrist instead of moving your wrist and whether you got an RP. But notice in our experiment, they were simply picking one of the letters on the screen, one of the 4 letters on the screen. They were not imagining moving at all. They were simply saying to themselves, I pick C, or I pick D, or I pick E. There was no imagination of movement in the task in our study, and yet we still found an RP.
Yeah, did you ask if there was some kind of sensation of the movement, a sort of a feeling of the movement during the no overt movement, just to know?
So we did ask, and the subjects reported, no, I didn't have an overt movement. But I'm a little worried about that because there was a kind of an experimenter demand. We told them, sit still while you're making the choice. And of course, if they sit still and they go, well, I kind of felt like I was moving, then they're admitting to us, they didn't follow the instructions. So they might be reluctant to say that when it might really be going on. I don't think this experiment, like every other experiment, doesn't prove a lot just by itself. It needs to be replicated and tried in other groups and with other setups. But they at least told us that they did not move, did not feel like moving. And we told them, like, don't point at the letter with your mind or something, or imagine yourself pointing with your finger. And they said, no, we weren't doing that. But how much do you trust self-report?
Yeah, just a final comment about the possible EMG activity without any overt displacement of the fingers and hand. Did you check with EMG recordings this possibility?
No, in the non-motor case, we didn't have an EMG on their hand because the instructions were just don't move your hands at all. Maybe we should have. I mean, that would be an interesting test to add. At least by self-report, there was no reason to think that they were moving their hands and pointing towards one of the 4 letters. There were just 4 letters on the screen, and they were in their minds thinking about it. By the way, of course, there's activity in the brain. Nobody's denying that. The question is whether there's any external physical movement. Yeah.
Thank you very much.
Sure.
Okay. Thank you, Claudio. All right. Should we try to switch to the more general discussion? So right now, the idea is to bring together your 3 talks and for everybody to try to try to bring those ideas we've heard today so far and get you to discuss about this. One question that actually was brought up quite a lot is so how do you draw the line? And or actually, let me bring Leon on stage if that's quick enough. It's always a bit. We're always waiting a little bit, but okay, it's good to be silent also sometimes, a little bit.
We should meditate for a while.
Yeah, well, let's think about what we've heard. Hi, Leon.
Hey.
Okay, so, go ahead with your question.
So the question was for Edison about the idea of highlighting a point in the data, and Max actually pointed to it in one of his comments, and it's always a tension between wanting to make your important finding easily visible to the reader versus actually biasing, and that goes to my else talk, biasing the reader or the viewer towards what you're actually trying to convince the reader of, right? So how do you draw the line between showing the data, allowing the reader to actually come to their own conclusion, and highlighting the thing that you want to highlight?
It's another fine line to walk here.
Yeah.
What do you think, Madison?
Yeah. Can you guys hear me?
Yeah.
Okay, cool. So there's two questions you can kind of ask yourself about this. So one that is really, really critical, I cannot emphasize this enough, is was there an algorithmic or like a statistical conclusion obtained? And if yes, then you really just want to highlight that solution. It almost becomes more of like a flagging issue there rather than like an exploratory data visualization problem. But if there is an exploratory element, or like if it's you like opening up your data set for the first time, if it's you and your colleagues trying to have a conversation to interpret something visually, yeah, then it becomes quite tricky. I think you sort of start with the curse of knowledge question that we find from Cindy's work, and just like examine your own biases, like going back to Manuel's talk. Try to think which of those you're carrying into the situation, and then try to rely on your low-level perception, like with the encoding you choose to explore and find the interesting artifacts. But as Walter was just mentioning, it's really important, if it is uncertain, there's no statistical evidence supporting some specific conclusion you're drawing, that you replicate in different situations, that you consider the method that was used. That question gets like quite large and quite beyond the scope of simply data visualization quickly, which is why I say like there are different processes to consider. Like, is this exploratory? Is this presentation? Does all the data matter? Does a subset of the data matter? You really want to lay these things out for yourself before you pick your encoding.
If I may, I think you're making a distinction between your exploratory phase and your presentation phase as it evolves in the course of the research, from the lab to the paper to the presentation. But in fact, the most important distinction is whether you have a priori hypothesis, real a priori hypothesis, which allow you to pick up specific data points and put aside from your whole data, or if it's really an exploratory research. If it is an exploratory research, then there's a big risk when you actually pick up just the important part, even if it's supported by statistical analysis, which we know all the policies of statistics. So just as people know the famous article, How to Lie with Statistics, we also lie a lot with, quote unquote, with the way you visualize your data. So I think that's an important, I think this is maybe the more important point, that whether do you really have a priori hypotheses or whether this was an exploratory research.
Yeah, absolutely. Like, a visualization should not give you an algorithmic answer unless it's like exceedingly obvious, like comparing two bars in a bar chart or something. But you should always have some kind of hypothesis that you're testing with statistics in science, certainly, if you want to draw a generalizable conclusion. Visual analytics is just one piece of the puzzle that can help you get to that point. So yeah.
Thank you. Thank you, Leon. Let me send you back to your seat. All right. Any other questions? Well, we have one here for Walter, and let's also invite someone on screen. For now, it's still fun to bring everybody and listen to their questions.
After we've got audience questions, I've got some questions about data visualization.
Oh,
too.
yes, please.
But
please, okay, yeah. In one moment. And but I'm sure I would like to hear you three. So you three there's one here, and one here for me. Talk together also, that would be great. Is the person I haven't, yes.
Hi.
Oh,
Hi.
Leon.
Thank you.
And
I just saw you a couple of days ago.
that's true. And to follow Leon, who was my supervisor, it feels like a family conference.
It's a family meeting.
So basically what I wanted to ask, thanks for the talk, it was great. But it also, I think, showed me that maybe our ability to find these fallacies is somewhat limited. So it's one thing to see you present the fallacies and understand them. Mm-hmm. It's another thing to detect them ourselves and not have them in our interpretations. So is there any advice you could give those of us who didn't study philosophy or who are not experts in detecting fallacies to avoid those in our interpretations? And of course, there is no recipe, but any advice would be appreciated.
I mean, I think, a number of bits of advice would be, spell your argument out carefully, step by step, and check to see whether it's valid or not. I've got a lot of books and MOOCs and stuff on that, learning how to do that. But the other thing that's maybe more practical that doesn't take as much time is ask other people. Other people are really good at seeing the fallacies in your argument. They're going to be much better at you. They're going to be your best friends in learning about this. And then the third bit of advice I would give, contrary to some people in the US today, is don't fill your lab with people who agree with you. Get people in your lab who have a very different perspective than you do. Mm-hmm. Some people tend to, hire RAs and grad students and postdocs who, they're just beating to the same drum as you. That's not going to help you find mistakes in your reasoning. You want to have people who are going to see the mistakes and be willing to speak out. So the way you set up your lab actually makes a big difference. And it shows then that, my lab is here to find out the truth. It's not here to show that this theory is correct. That's the kind of, you do not want a lab of the second sort. You want your lab to be the first sort. We're here to find out the truth and we're going to listen to each other. So I think labs, but also colleagues, the same thing. Make friends with the people who disagree with you.
Mm-hmm.
Thank you.
Thank you, Liad. Okay, so yeah, you're welcome to talk together also. Walter, you said you had the question.
So I always worry about data visualization. The question that came in was about, you've got your own hypothesis. You want this to be true and you try to show that it's true. Do you focus on that or all the other things? I want to ask, how do you present it when you get something that's true? Because I do a lot of surveys with Likert scales, 1 to 7. Answers, and then we put them up, the results up in bar graphs. And I always have, people who say, oh no, all the answers were between 4 and 6. So we're only going to have the y-axis show 4 to 6. And then it looks like this gigantic difference between the two bars. Whereas if we did 1 to 7, it would look like a small difference between the two bars. And yes, it's right. Yes, it's statistically significant. But how you present it can make the effect size look a lot bigger than it really is. Is that fair? Should that be avoided? Should journals have as a policy never accept graphs that don't show the full scale on the y-axis?
You know, I think if you ask different data designers, you'll get like wildly different responses. I'm a big proponent of building your narrative. This is way beyond the scope of visualization, but I teach a research methods class, and I teach a section from this book called Houston, We Have a Narrative. Marine biologist Randy Olson switched to working in the Hollywood film industry. And what he kind of noticed was that like really successful science papers follow the same narrative that really successful Hollywood movies follow. You kind of start with like the normal state of affairs. Like he uses The Wizard of Oz as an example. He's like, okay, so we start in Kansas. Kansas is boring. It sucks. Then there's this like tornado. The house falls on the ants, and then Dorothy gets sent to Oz, right? And that's kind of like a competing piece of evidence, right? That comes up for you in science. You're like, oh no, like I'm in Oz now. Nothing that I believe makes sense. Then you have to like follow the yellow brick road or like do your experiments. And you know, eventually you're going to come to some conclusion, right? Like Dorothy clicks her heels 3 times and finds out there's no place like home. Kansas isn't so bad after all. Like in science, we find out like we can add to our theory or extend our assumptions. And now we know what the state of affairs in the world should be. And so I sort of believe in charting out what that narrative that you're trying to convey in your paper publication is before you pick your complementary visualization. Maybe it's okay to like make your effect sizes look super big visually because they're supporting like a very beautiful structure that's going to engage your readers and, you know, get people like to consider your points so they can run follow-ups. You should never be cheating people with data, certainly. But if it helps people to understand what's going on, that can be really powerful. I can share my screen. Yeah. Quickly, I want to show a really famous visualization that kind of like, I think it's a perfect metaphor for what we should do in science. So back in the mid 1800s, there was a big cholera outbreak. And this scientist, John Snow, had a theory that it was coming from this pump, that there was basically contaminated water. And so he could have like gone around and taken water samples, but what he started doing was actually plotting the number of cholera cases geographically. And what he finds is that they're all clustered around this Broad Street pump. And that like saved him a bunch of time because he didn't have to go around and systematically test all the pumps in the city. They could just test the water at Broad Street and make interventions there. And like, sure enough, they discover that, yeah, that's the source of the cholera outbreak is that specific well. And I think that's like a really beautiful interplay because it's like, yeah, data visualization, it got him to the right answer. It saved him a bunch of time, a bunch of complexity and confusion, eliminated a bunch of competing hypotheses, but it didn't give him the answer. Like they couldn't make a public health intervention just based on that map that he drew. They had to actually do some kind of rigorous scientific tests. And that's sort of the place that I think data visualization sits best and like where it's best executed.
So I want to ask a follow-up question. Early on, what you said was, you know, a successful science paper is like a successful movie. But wait a minute, what counts as successful? If success in science is getting other people to listen to you and cite you so you can get tenure and, you know, make it to the National Academy of Sciences or whatever, then that's one kind of success. But the other success is getting it right. And sometimes a really good story is going to lead you down the wrong road, not the yellow brick road, but whatever, some other wrong road. And so how do you tell whether the story is sounding good and other people are going to go along or whether you've got it right?
That's a great question that I think I'm, you know, at least in my young part of my career, I'm definitely still trying to figure out. I mean, I think almost any like major effects that I know about in vision science has like the place that it first emerged, like, which is some probably not very highly cited paper where they just like found this thing to begin with, but it wasn't part of their primary argument. And then it has like the big theory that someone gave like a very sexy name to and like very concisely, you know, wrote it out and explained. And I think the question you're asking is like, is that problematic? Like, should the earlier thing get the credit? Like, can we pull these findings out and like highlight them earlier? And I don't know that the scientific method, which I do trust, like gives us a ton of like success criteria, or like a ton of like easy way to do that. I think it is part of like experimentation. The process is all about experimentation and failure, and like just trusting your data and listening to it in a very honest and open way, and being willing to change your assumptions and your worldviews. But you know, you're more senior than me. I don't know if you have like your own feelings on what the answer to that is.
I mean, I think, you know, I totally believe in the scientific method. I think the problem is that these days, people write small incremental papers that build on pre-established techniques using methods and theories that other people buy, and you can't get published in journals otherwise, because you'll have reviewers who go, "Oh, you're just doing it all wrong. You don't know about this theory and that method," and so on. So you've got to kind of stay within these confines. I think sometimes that really slows down science and prevents larger, quicker leaps into more accurate theories, because you have to stick within what's common in order to be successful in the field. And I think your analogy to a story is like that. It's like if you have a story and then all of a sudden something goes off to the side and it's totally different, then people go, "Oh, whoa, that's not a very good story. It's not coherent." We want it to be like this progress along a road, instead of, "Hey, maybe we should go back and think about whether we ought to be on this road in the first place."
Yeah, I think that's absolutely true. I mean, back to Manuel's presentation, like confirmation bias rules our lives, and it's really hard to break out of that, especially when you've built, you know, a 30, 40-year career on a set of findings that you continue to replicate, and suddenly there's like competing evidence or a different explanation for the same data. And yeah, I don't know what the easy fix for that is, but that's kind of like the excitement in science too. So
yeah, I mean, it is. It's a lot like confirmation bias, but confirmation bias is supposed to be a bias that we all share kind of biologically and psychologically. I think it's also built into our institutions. The way science is done and the way journals decide which articles to publish and which ones to reject, creates the same kind of effect.
Yeah, I totally agree. I think the open science proponents are doing a really great job of like raising awareness about this, but I haven't seen like an easy parsimonious solution that, you know, I think we can all definitely adopt. I do like, you know, claiming what your confirmatory hypotheses are ahead of time and being quite honest about what your exploratory analyses were, reporting them as such. I wish people would take those exploratory and confirmatory hypotheses and findings like more seriously. Hopefully in the next 5 years, we'll start to see people like a little bit more open-minded towards that. Yeah, but I think it's a problem.
I have a question for Walter, actually. It seems that it's like we relate some of the mistakes that we are doing as scientists to our era, like the modern era, like industrial, whatever. But Walter, do you think the fallacy that can bias us today were the same than the one that were the same that the one that were inducing bias like a century ago or like 10th century ago? Do you think that we are subjected to the same type of fallacies?
Yeah, I mean, it's certainly there are continuities there, but think back to the great scientists who made really groundbreaking discoveries. Darwin, you know, he didn't have to like go out and apply for grants and worry about whether he was going to get published and work with this giant lab. I mean, he did have a lab and he worked with some people. Or Madame Curie, she stuck then and did all these things one after another when they weren't coming out right, and just kept going and going and going and did these great discoveries. And Newton, and it's not like he had to worry about getting tenure. I mean, it was, I think a lot of the pressures that scientists face today were not faced by a lot of the great scientists who made the really big discoveries throughout history. So there are differences as well, but I grant you there's a lot of continuity.
But the narratives that they were all they had to put together in order to bring these big discoveries was still quite important, right? And about the way we tell about science, we tell a story. It's also very important because it makes it captivating and it gets attention. And even though getting attention is not the only goal of science, still, if you don't get attention, your ideas don't spread. So I really wonder, I mean, there's really, again, this tension we've been talking about already a couple of times between making it sound fancy, but perhaps not so rigorous in terms of reasoning, and making it very rigorous, but dry and ununderstandable. I don't know. Do any of you have any comment on that? No.
I mean, to succeed, you have to be able to tell a good story. There's no doubt about that. But then it makes me wonder how many really great experiments there are out there with really fascinating results, but the author didn't know how to tell a good story, so nobody's paying any attention to them. You know, they're like
forget the author telling a good story. How many of them are sitting in a file drawer, right? Like, they may not even be in a journal. Yeah.
Absolutely.
And I think, Max, we discussed the fact that as a researcher needs to have many skills. It's not because someone is a good mathematician that he will be a good storyteller. And it's the same thing, like people are good to write grants, but they may not good to do some EEG recording. So maybe researchers are also facing the complexity of their job. And we could imagine that in a team, there will be one person that will actually be the storyteller, and another one that will be more specialized in something else. And that could be also a way, if we go back to what we have said before, especially Walter, when you said hire people that think differently than you, maybe also hiring people that have different skills. They can still think a little bit the same. We can discuss about it, but with different skills, like someone who is really good in data visualization, someone that is really good into communication, bringing grants, and sometimes, that may be one of the possible future of our work, is to just to acknowledge that, okay, I'm good at speaking with a French accent, but I might not be good to ask questions. I don't know if, yeah,
I think that's right. And working with other labs too. If you know that somebody in this other lab that's not working on your topic at all is really good at data visualization, like email her and go, how should I be presenting this? And then if we can get labs helping each other, we will often be able to find people who disagree with us more often, and avoid a lot of mistakes, and hopefully do better and more productive science, including science that will make bigger changes instead of just incremental moves.
Yeah, we have a new question coming up in a few seconds. But Manuel, if you had a further comment.
I can wait later. It's a question for Madison if we have time.
Okay. Right, and we're getting close to the end of the session, and I hope. No, she's not coming on stage. Okay, several years ago, I've learned about. So I read it for Rasa Gulbinaite. Several years ago, I've learned about virtual reality as means to represent the neural data, 3D reconstruction of neurons and glia and their interactions. Do the speakers think that virtual reality could be used to explore the data, be it neural or not?
I'll take this one. Sure. Yeah, I think VR shows a lot of potential these days. At Google Maps, they're actually trying to integrate VR into the live view when you're navigating. I don't know if you've ever had the experience where you're looking at the blue dot on your map and you're do I go left or do I go right? I don't really know if my GPS is oriented the right way. And you probably just start walking down the street only to realize like 2 blocks later that you've been walking the opposite direction that you're supposed to. So they're trying to integrate VR so you can like hold your phone up and it like gives you like an arrow in the display to like point you the right direction. Like, I think that's like quite successful, like data visualization in VR. So I think people are just starting to like have good, clever thoughts in this field. I'm super excited to see where it goes. But of course, 3D visualization is a real can of worms. Our visual system does a lot better with like processing low-level features and like making these like graphically 2D comparisons quickly. Like the 3D world and adding depth perception and like individual differences, it just gets quite complex quite fast. So I think finding like patterns and heuristics that are simplistic are going to be the place to start, even in a VR environment, and not trying to like simulate living inside of a 3D brain or something crazy like that. I think that'll be a total disaster. Yeah.
Yeah. Thank you. Any other comment? The two others?
Madison, we discussed, to prepare the meeting, we discussed about data visualization in EEG and MEG. And back in the days, but I think they're still doing it too, when the researchers are recording the neurons in monkey's brain, they are using they are listening to the spikes in order to define what the neuron is coding for. And I was wondering if, in your experience, I know you are a visualization data scientist, but when you have interact with other people, like in Google or in your lab, sometimes do you use not data visualization, but I don't know if there is a proper word in English to say data audio something, like to use auditory inputs to, because like when we park a car, for instance, we hear the sound that codes the distance with the car behind. Is there any other or like fancy use of the auditory system that you know of?
Yeah, there's a few people that are interested in multisensory visualizations. I'm not super well versed in the field, but I see it every year at the IEEE Viz conference, and it's like very cool. Our auditory system is not quite as precise at a lot of these like psychophysical tasks as our visual system is. Our visual system is very precise and very accurate, fortunately. So I think like multisensory could work because they're complementary, and maybe it's just like a redundant encoding reinforcing an idea. I don't know that I'd want to rely totally on our auditory system for getting like the full story of information. Yeah.
I mean, some psychology experiments have suggested that when you put auditory together with visual, you get distortions, often called the McGurk effect, where you might be seeing one thing and hearing another, and your mind processes it as something in between, which is, of course, not accurate to either of the actual signals. So I think that's just a warning. You got to be careful if you start integrating auditory with visual signals.
Definitely. Yeah, that's like very uncharted territory still. I think they're still trying to figure out like what the match is just in like low level like sensory information. So yeah.
Okay, I think it's about time to close this session. I want to thank you all three, first of all, for the very nice presentations and the discussion. And for waking up very early overseas there, I know that. So thank you again. I'm going back in the main room, although there are some who are preparing the next session here. So I just want to close this session saying goodbye to you three. And I just wanted to make another point. Please keep in mind that we are actually editing a special issue of the paper NeuroImage in the coming months and the coming year. This is an invitation to you three, but to also any other people interested in the field of good practices for EEG and MEG research. Please submit your paper. I know I've been talking about this with Walter, with Manuel also, not specifically with Madison, but we would be really thrilled to see your papers coming up there. And thank you all for listening. I leave you with a little view of Marseille, and we'll talk to you soon. Okay, look at this, isn't it nice?
Ah,
Wow,
there.
beautiful.
Okay, enjoy, take care, and see you soon.
Thank you. Thank
Okay.
you.
Thank you very
everyone.
much.
Thank you,
Bye.
guys. Bye bye.